Now let's look at Fick's law for molecular diffusion. So somewhere around 1855, Adolf Fick's proposed that diffusion or molar flux of a species A is proportional to the concentration gradient in a certain direction for an isothermal isobaric binary mixture is indicated by the equation 1.21 there. Right. If we are to, we can then now remove the proportionality constant there so as to and replace it by diffusion coefficient. By diffusion coefficient or diffusivity, which is DAB, and this is also again for a binary system. So if that's achieved, then our JA, indicating that we are talking about species A, is equal to minus DAB DCA DZ. Then our negative sign there, since we are moving from a region of higher concentration to a region of lower concentration, this differential will result in negative. So for the physical quantity to make sense and applicable, we introduce a negative sign there so that this is computed as a positive value. So a more general equation is the one which is not making use of the restriction, which makes use of our more more fraction there, which is dy dz, and basically this is obtained, or you can arrive at this equation simply by knowing that C A over C total concentration is equals to our mole fraction there. Then employing our differentiating both sides, you'll be left with your dCA equals to your C, because that's a constant, and your dy there. Right. So moving further, if we now look at an example that was extracted from a book written by written by Jean Coplis, which is transport processes. So here we have we want to determine the steady-state diffusion flux of helium in a binary mixture with nitrogen. The mixture is contained in a pipe at a constant temperature of 298 kelvins and a total pressure of 1 atm over a distance of 0.2 meters. The partial pressure of helium decreases from zero point 0.6 to zero point 0.2, given a diffusivity of 0.687 times 10 to the power minus 4 meters squared per second. Calculate flux in both SI and CGS units. So let's extract the information that we have there, our R, the gas constant, the temperature, our total pressure given as 1 atmosphere, our partial pressure, point 1, partial pressure point 2, the given diffusional constant, JB, Z1, Z1 at point 1, Z2, at point 2 there. Then solution to that, let's make use of a diagram. Is fig 1, 2, one pipe there, and we have our points, and we add the relevant data to that there. Is the Z1, Z2, so that's easier. So you'd find that our data is given in form of partial pressures there, so it will be easier to employ the equation that makes use of partial pressures there, and that will be far much easier, as you can see there. So remember, we are moving from a scenario where we have our equation there was J A is equal to your minus D dy over dz. So there should be a C there. I've left out a C there. So C, so, and we put our negative. So they need to replace this using the relationship between partial pressure and mole fraction. Then we arrive, after integrating that, we arrive at this equation. Then you'd find that our DAB, we have PA, we have PA2, we have RT given T given Z2, Z1, all we have. So it's now a matter of us just substituting the known values into this equation, then computing that as indicated there, and we get our solution of 5.61923 times 10 to the power minus 6. So this is an SI unit, and CGS unit there is 5.61923 times 10 to the power minus 7 gram per square centimeter second. So our Fick's law can be written in equivalent forms. So here we have presented the differential form and the integrated form there, and we have our mole fraction form, concentration form, partial pressure form, and mass form. So this, you can choose which one to use depending on available data from your problem or scenario, or you can just move from one form to the other through manipulation.